Today I'm going to explain the Millikan oil drop experiment. This is an experiment that was performed by Robert Millikan and his colleague in 1909 in University of Chicago, and he got the Physics Nobel Prize in 1923 because of his work. For the first time, he was able to measure the charge of electron, and the final value that he reported was negative 1.592 times 10 negative 19 coulomb. And if I want to compare this value with the accepted value today, that is a negative 1.602 times 10 negative 19 coulomb, you see that the error is the 0.6%. So it means that it's a almost very small error. So here's a very simple apparatus that I'm going to explain you, and then I will tell you about the formula. And in the next video, I will show you the setup that we have here, and of course, I'll use it to determine the charge of electrons. Here's a very simple apparatus, a type of box. There are two metallic plates here, there are horizontal metallic plates here, they are connected to a battery. It's possible to change the polarity of the battery, and there's a switch here. So we see that this one is a type of parallel plate capacitor. Then he used oil, very special type of oil, and then he sprayed the oils here. So in fact, this type of oil that the droplets are very, very small. Oil droplets are here. Before they enter this area, use the ionizing radiation source like X-ray, use the X-ray, but it can be anything, other sources to ionize these oil droplets. It's also possible to, by friction, also possible to these oil droplets be ionized. So we need a type of ionizing source. So when they enter here, there are charged oil droplets. They are not neutral like here. And the distance between the two plates is d. Now, if I close the switch, of course, based on the polarity, there's electric field here, up and down. So I will show you it's possible to keep these particles suspended, type of equilibrium, or push them downward or up, based on the electric field. Here's a type of light here, so that you can use the microscope and see these droplets. It's a type of cumbersome experiment. We have to spend time on it to measure the value of the electric charge of these oil droplets. And you have to do it 6 times. Millikan by himself measured it many times. So he spent some years to measure all of them, and this value that I told you was the final result and the best result of his experiments. Now let me focus on the formulas that you need. So they are simple that you have learned. I use a free body diagram. All droplets, we assume that there are spheres. It's a good approximation. Spheres, and the radius of them is r, and they have a mass. So this is the all droplets. So when they are falling, there's a gravitational force exerted on them, and also drag force. It's true that they are very small, but it doesn't mean that we can neglect the drag force. Drag force by the later. And because I assume that is a complete sphere, I can use the Stokes formula, Stokes law, to calculate the drag force. That is equal to 6 pi r eta Vt. Eta is the viscosity of air. Vt is the terminal velocity. So because when they drop very fast, they reach the terminal velocity. So before we close this switch, there are neutrons. They are not neutral, of course. There is no electric field. They just drop. And if we use this formula, and we can manipulate them and find the gravitation, of course. That is very important. That's equal to this expression. You see that this depends on the radius of these oil droplets, density of oil, and density of air. Then I can use this formula to calculate the radius of the this oil droplet that is equal to this value. It's possible to calculate the terminal velocity. We measure the distance here and divide it by time, so this one gives us the terminal velocity. So whenever I calculate the radius, so I can immediately calculate the force of the gravity. It's very easy. Then we close the switch and establish an electric field here and suspend the oil droplets. In that case, because they are suspended, there is no drag force because there is no motion. So speed is 0 and it's a gravitational force that points downward. Electric field should be points upward, and they cancel each other. Yeah, I wrote this one here. And because I assume that it's a parallel capacitor, let's write this one here. I know that if it is an electric field, something like this, E, we have seen that E is equal to delta V divided by D. So for parallel capacitor. So I can use this formula and find the charge. So charge is equal to force of gravitational force, which here, because I know the R. In fact, I should call it something. I should reverse the R. We can calculate the radius, and from radius I can calculate the gravitational force. So because they are equal, like we see that it's possible to calculate the Q, FGD divided by delta V. And we know what is the delta V, we know what is D for our apparatus. For our case, D is about 2 meters. Then it's possible to change the polarity and make it move them again, I told you. Give them acceleration upward or downward. If they are going upward, you have an equation like this. So drag force is here, or if they're accelerating downward, the acceleration should be, the drag force should be upward. This is the only difference between them. But we use mostly these two steps to calculate the charge of electron. We don't go to this step. In the next video, I will explain the apparatus to you and show you how we use it to measure the Q.